Hello dear students, welcome to the channel and welcome to the signal and system playlist in which we are discussing about signals and systems from very base, in which we are uh, discussing what is signal, what is system from very base, from very start. And up until now we have seen what is a signal, we have seen what is a system, we have seen different classification of signals. In that we have seen continuous time signal, discrete time signal, we have seen analog and digital signals, we have seen periodic and non-periodic signals, we have seen even odd signals. After that we have seen uh, energy and power signal, we have seen random deterministic signal, right? We have seen bounded and unbounded signals. After that we have discussed a few important signals, in which we have seen impulse signal, we have seen unit step signals, right? We have seen exponential signals, we have seen sine wave, sinusoidal signal, right? And after that we started discussing about systems. In systems we have seen what is a system, how the system works, how does it connects with signals. We have also seen different classification of systems, and today we are going to talk about different type of properties of my system. So let's start with the first one. The first property is called static and dynamic systems. By the way, if you haven't checked out previous videos, or if you have missed the previous videos, the link will be flashing on the top right corner of the screen, so you can see the previous videos and access the playlist from there. So now let's get started with the properties of system, general properties of system. So first is static and dynamic property of system. Okay, so firstly let's see what is a static system. So let's discuss it for continuous time system first. So any continuous time system is said to be static system if its output depends upon the present input only. Okay, so the output, if my output of my system is depending on the present input only, then my system is called static system. Okay, now how do you ask? So now let's consider a voltage drop in the resistor, which is depending upon the current, right? So how do you express it? So it can be expressed with the help of this equation: vt is equals to r into it, right? Here pay close attention that my output is vt, right? And the inputs are resistance r multiplied with I of t, which is my current. Now see, in my output, the variable t, the time t is only dependent on the time t of my current, right? So it is dependent on present input only, right? The voltage drop will change as the current will change, right? But it will not be like that I have changed my current an hour ago, so my voltage is changing now. No, it will not be like that, right? So it will be dependent on the present input of the current only, right? So if you change this I of t to I of t minus 5, then in the output side v of t will also change to v minus 5, v of t minus 5, right? Which means your output is depending on your present input only, right? And this static system, as it is only the output is only depending on the present input only, so it is also called memoryless system as well, right? You can also call it memoryless or instantaneous system as well, because your system is not remembering what happened in the past, right? It is only reacting to the present input only, right? My present value of current will only affect the present value of voltage, right? It will not affect the previous value, or the past value of my current will not affect the uh, present value of my voltage, right? So it is not remembering it. So that is why it is also called memoryless system. Now let's see what is a dynamic system. So it is complementary of a static system. So you can say any continuous time signal is said to be a dynamic system. Sorry, any continuous time system, not signal. Apologies. Any continuous time system is said to be a dynamic system if the output depends on the past values of input and the present values of input. Okay. Now again, how does it happens? So this time let's consider an example of a capacitor. What happens? How do you express the voltage across the capacitor? So we can express the voltage across a capacitor with the help of the this equation, right? V of t is equals to 1 by c integration minus infinite to t it into dt, right? What you are doing, you are uh, taking integration across the time, right? So what is happening here? How my voltage is coming, right? The voltage across the capacitor is depending on the present values and the past values, right? Because if it was only the present value, the integration wouldn't be here. We are also considering the past values of current, and because of that, because we are having integration sign, right? What does integration indicates? Integration indicates the system which is having some memory, right? Integration indicates the system with memory. So what is happening here? We are taking integration, so that means we are considering something. We are calculating the area in the graph. If we plot a graph, we will be calculating the area in the graph, right? So such system, we call it dynamic systems, right? What happens there? The output will depend upon the past values of input and the present value of inputs, both, right? So now this was about the continuous time systems, right? Now if I want to go for discrete time system, what will happen? So it will be similar to the continuous time signal as well. Instead of continuous time values, you will be having samples. So the discrete time systems can also be either static or dynamic. And if output of the discrete time system depends on the present input sample only, then it will be static, and otherwise it will be dynamic, right? So pretty much clear and self-explanatory, right? So let's say y of n is equals to say some value, right? Like how do you say my system is dynamic? So let's say my output for a discrete time signal, the output will be depending on the past values of the input samples, past value of input samples, right? In continuous, what did we had? Past value of time, because we were having continuous signal, past value of signal, right? But we are having uh, samples, so we will be considering past values of input samples, right? So how do we express it? So you can say y of n is equals to x of n plus x of n minus 1, right? So see here, y of n is my output, x of n plus x of n minus 1 is my input, and this x of n minus 1, what is it indicating? It is indicating the value of the one value before the present value, right? If let's take n is equals to 4, if my n is equal to 4, what does it mean? It means the fourth sample, right? So uh, x value of the fourth sample plus x value of n minus 1 means 4 minus 1 is equals to 3. So x value of the third sample. So see what is happening. Third sample is my past input, right? So uh, my output is dependent on my past input sample. So what system this will be? It will be a dynamic system because output is depending on my past input, right? And it is quite easy to determine if the system is static or dynamic, because how do you see it? Whenever you see any integration sign, if you see a differentiation sign or you see any delay, right? Or even if you see summation sign, sigma sign, so all those signs are direct you toward the dynamicity of your system. It indicates that your system might probably be a dynamic system, right? And that was for the continuous time signal. For discrete time systems, what do we see? We see if the in the value of my signal, if it is having value which is having minus or plus, like here we had n minus 1, right? See, like that. So that was static and dynamic behavior of my system. Now let's see the second one, time invariant and time variant system. So what system is called to be a time um, invariant system first? So let's again first see for continuous time signal. Sorry, continuous time system. So for continuous time system, continuous time system is a time invariant system if the time shift in the input signal results in the corresponding time shift in the output signal as well, right? So what you are doing, if you are delaying your signal, if you are delaying your input with let's say 5 seconds, then your output will also delay with 5 seconds. If you are facing the change in the output, that means your system is what kind of system? It is time invariant system. It is time invariant system. Why? Because what is happening here, your input signal, the time shift in the input signal is resulting in the time shift in the output signal as well, right? So if you are delaying your signal by 3 seconds, or if you are delaying your signal with 20 microseconds, then your output will also delay according to that. If you are delaying 3 seconds, then it will, your output will delay 3 seconds, according to that, according to whatever scaling you apply. It's not necessary it will be delayed by 3 seconds only, but according to the change in input, your output will react to that. So if you are having such system, then it is called time invariant system, right? Now let's see mathematically what happens. Let's take a system in which y of t is my output and f of x of t is my input. Okay, so if x of t is delayed by time t1, then my output will also delay by the same time, right? The output will delay by the same time when when my system is my system is having time invariant property, right? So what will happen, if my if I give the t1 delay, so here I have given this t1 delay to my input signal. What I've did, f of x of t minus t1, right? I'm giving some delay, so my output will also be delayed by t1. See, y is equals to t minus t1, right? And similar thing will happen for my discrete signal as well, right? What will happen in the discrete signal, I'm delaying my sample by few number, k number, let's say. So again my output sample will also be delayed with the k samples. Okay, and because of this change, like when change in input takes place, output is also changing. Because of this change, the time invariant system are also called the fixed systems, right? Because uh, uh, as you change the input, your output is also changing, right? So it is called fixed systems, right? And then let's come to the other one, the time variant. So what is the time variant property, or when do we call a signal a time variant signal? So when the time shift in the input signal does not result in the corresponding time shift in my output signal, right? Which means I'm changing, like if I'm giving the 5-second delay to my input, then the output is not changing. Output is remaining as it was before giving the delay. Then my system is called time variant signal, right? what will happen if my see here in the example what I have done. I have taken I have given t1 change in time, right? I'm given t1 delay to my signals. And what is happening here, see, I'm not getting any delay. I'm not getting any delay, which means y of t comma t1 does not equal to y of t minus t1, right? That makes my signal a time variant signal. Or in other words, what will happen, like say if I took a system and I delayed my input signal with let's say 20 microsecond, okay. Or for instance, if my system is that large, so I'm giving my signal a time delay of 3 seconds, but my output is remaining as it is not getting delayed by 3 seconds. That means my system is a time variant system, because no matter how much changes I am putting in my input signal, my output signal is staying as it was before giving the delay, right? So that is the property of time variant signal. And how do you find if my system is a time variant or time invariant? So you do just that you are you just give a delay to your system, delay to your signal, and you check if the output of your signal is changing as well or not. If output changes, then it is time invariant. If the output does not change, that means your system is time variant system. See, like this, y of t minus t comma t1 does not equal to y of t minus t1, that means your system is time variant system. And y of t comma t1 is equals to y of t minus t1, then your system is called time invariant system, right? So that is your time variant and time invariant property. Now let's come to the third property, which is called linear and non-linear system. So simple linear system can be explained very simply. If my system follows the superposition principle or superposition law, that means my system is holding a linear property. uh, I hope you all remember what was the superposition theorem. If you have learned circuit networks, in that you may remember. And even if you don't remember, I think linear property is pretty much self explanatory, right? You have two different variables. On the x axis we take time, on the y axis we take my signal, the amplitude of my signal. And if it is giving linear output, then it is linear system, right? Then again, let's see how do we verify it. So first let's see for the continuous time signal, right? So how do we define it in a continuous time signal? So for that, let's consider two systems. We are taking two systems. The first system we are calling the output of the system is y1 of t, and the input of the first system is x1 of t, fx1 of t, okay. And the output of second system is y2 of t, and the input of the second system is fx of t, fx2 of t, sorry, fx2 of t, okay. Now these two systems will only be called a linear system if and only if they satisfy this given condition. See here, we have given the condition that f of a1x1 of t1 plus a2x2 of t2 should be equal to a1 into y1 t1 plus a2 into y2 t2, right? That is your superposition theorem. And if your system satisfies that, that means it is a linear system, right? And if it doesn't satisfies that, this uh, if your system does not satisfy this condition, then it is a non-linear system. Now let's try to see it for a discrete time system. Again, for discrete time system, let's consider two different systems with again similar outputs and inputs. So for the first system, we are having output as y1 of n, and we are having input as fx1 of n. And for the second system, we are having output as y2 of n and input as fx2 of n. And again, the discrete time system is considered linear if and only if it satisfies the following condition that is given here. What is the condition has been given? See, f a1 x1 of n plus a2 x2 of n is only equal to a1 y1 of n plus a2 y2 of n. If this condition is getting satisfied, that means your discrete time signal is a your discrete time system is a linear system. Okay. And if it doesn't, then it is your non-linear system, right? It's pretty much straightforward for linear and non-linear systems. Now, one more important point. So a linear system produces zero output if the input is zero. Okay. And under the relaxed conditions, if you are not providing any input, then your output will be zero, but still it is said to be a linear system, right? Because what if you plot a graph of such system, what will happen, right? At some point your the linear graph, the line will go through the origin point as well, right? So that is the origin point condition, right? You are not having any input and you are not having any output, right? So that is also in the uh, linear system properties. Now let's come to the next one. We are having causal and non-causal systems. First, let's see what is a causal system, then we will see non-causal. So the system is said to be a causal system if its output at any time depends upon the present and past input only. Okay. So output at any time is depending on my present and past input only. So remember the example of capacitor. In that, what was happening? Your the output of your system was depending on the present and past input only, right? That means your system is a causal system. Okay, your system is a causal system. Now let's see the condition for the continuous time signal. What is the condition? So y t0 is your output. So y t0 is equals to f x of t, where t less than t0, right? So what it says? So it says output at time t0 will be dependent on the input before the time t0, right? Means this system is not it's not anticipatory, right? Output at time t0 is depending on the inputs before t0, right? And what happens for the discrete time systems? Again, for discrete time system, what we how do we define the condition for causality? So it will be y of n is equals to f of xk, where k less than n. Okay. So the output is the function of x of n, then x of n minus 1, say x of n minus 2, x of n minus 3, up to, right? So that will be the output for causal system. Okay. If your output depends on the future input as well, that means your system is non-causal, right? In causal, what did we say? Output at any time depends on the present and past inputs only. But for non-causal, what happens? Output is depending on future inputs as well, right? So output is a function of x of n plus 1, x of n plus 2, x of n plus 3, right? So that what are they? They are your future inputs. And x of n minus 1, x of n minus 2, x of n minus 3, when you are having minus, that means your past inputs are coming here. X of n is your present input, and x of n plus 1 plus 2 plus 3, they are your future inputs. So whenever you see that your system is depending on the future inputs as well, that means your system is a non-causal system. Okay. Again, there is one more important thing in practical situations, in practical scenarios. Whenever you have to distinguish between causal systems and non-causal systems, always make sure, because there is no such system as non-causal system, right? Because there is no system in practicality that exists that whose output depends on the future input, right? There exists no system whose output is dependent on the future input. So all practical systems are causal systems. The non-causal system in practicality does not exist, but in theory it does. Okay, so um, all causal systems are physically realizable. And again, the non-causal are physically not realizable. Okay, and again, how do you distinguish when you are calculating the sum? Whenever you see in the output you are having if your output is depending on x of n plus 1, n plus 2, n plus 3, that means your system is a non-causal system. Okay, now let's see stable and unstable system. So for that, let's see what is a BIBO system. BIBO system means bounded input bounded output system. Okay, so to be your system to be a stable system, your system must be a bounded input bounded output stable. Okay, so when every bounded input produces a bounded output, then the system is called bounded input bounded output stable system. Okay, when every bounded input produces bounded output, at that time only your system is called bounded input bounded output stable system. And this criteria is applicable for both again continuous and discrete time systems. And the input is said to be bounded if there exists some finite number, let's say mx. For that mx, this condition gets satisfied. What is the condition? So x of t, modulus of x of t less or equal to mx, the finite number which I was talking about, and less than infinity. Okay, this was for your continuous time input. And what will happen for discrete time input? So here we will have a sample instead of signal. So x of n less or equal to mx less or equal to infinity. Now similarly for output, what how do we say if it is bounded or not? So again we will have some finite number my in this case. Okay, so we will have some finite number my. For that, your output will be the modulus of your output. Your output is y of t for continuous time output, and for discrete time output you are having y of n as your output. So modulus of your output, which means modulus of y of t for continuous time, less or equal to my less than infinity. And again for discrete time output, modulus of your output, which is y of n. So modulus of y of n less or equal to my less than infinity. That is your that is for outputs, right? And when do you call your system an unstable system? So if your system produces unbounded output for even the bounded inputs, then your system is called unstable system. Okay, when your system is producing unbounded output for bounded inputs, at that time your system is called unstable system. Now let's see what is invertible and what is inverse system. Okay, so a system is said to be invertible if there is unique output for every unique input. Okay, there is unique output for every unique input. So if you are entering x of t, then your output is y of t. If you are entering x of t plus 1, your output is something else. It should not be the repetitive output. Okay, it should not be like if you are entering x of t then output y of t. If you are entering x of t plus 1, then output is y of t again, right? Your output is should not repeat. If your output is getting repeated for unique input values, that means your system is not invertible. Okay, if you have unique output for every unique input, that means your system is an invertible system. It can be inverted. Okay, so let's come to this figure. So what is happening here? If the system is invertible, there exists an inverse system. Okay, if my system is non-invertible, that means it cannot be inverse system. only if my system is invertible system, then my system can be an inverse system. That is, this is the tricky part here. See, among all the type of systems, all the properties of systems which we have seen up till now, it was they were having complementary relationship, right? Like either my system is stable or my system is unstable. Either my system is causal or my system is non-causal. Either my system is linear or my system is non-linear. Either my system is time variant or my system is time invariant. And either my system is static or my system is dynamic. But for the invertible and inverse system, my inverse system can only exist if the system is invertible. If my system is non-invertible, then inverse system does not exist. If my system is non-invertible, then it is non-invertible. Okay. So if the system is invertible, then only my inverse system exists. Okay. And what happens when you multiply to your original system with the inverse system, and you get the original input as your final output, which means your input and output are same, then your system is called to be an inverse system. Okay, that is why I have drawn this uh, blocks over here. I have drawn this figure over here to make you understand that. See what is happening here. You are giving input x of t to your system. Okay, then you are getting an output y of t. This output of your system y of t, you are giving it to your inverse system. And if you are getting the if you are getting the final output as your original input signal, which was it, see here, it was x of t, that means your system is called inverse system, right? In theory, how do we define it? So if these two systems, your system and invertible system, are cascaded together as shown in figure, then output and when the output will be same as input, then your system is inverse system, right? And if the system is let's say if I'm denoting my system as h, okay, and if my system is denoted by h, what will be the inverse system? It will be h inverse, right? So what will happen when we multiply those two systems, when we cascade those two systems together? So we are taking h into h inverse, we will be getting 1 as an output. Okay, we will be getting 1 as output. So what we are doing, we are taking multiplication of my original system h and the inverse system h inverse. So when we multiply both of them together, we will get 1 as an output. Okay, that is also one of the property of inverse system. So that was it. That was the different type of properties of system. These type of properties are very basic, very fundamental thing if you are moving forward with signal processing. So uh, if you are looking forward to make a career in signal processing, you should not stop here. Please try to do as many examples, as many numericals as possible. Try to simulate try to simulate these properties. Try to verify, check these properties by different simulations in MATLAB as well. And by doing that, you will get to learn a lot. You might learn few more things by doing that. So I encourage you all to do that. And about this lecture, if you have any doubts, any queries, or if you have any feedback regarding this lecture or this or the previous lectures, or the entire playlist, please feel free to mention them in the comment section below. uh, we are ending this chapter with this lecture. Next time I will be presenting you the very next chapter, the second chapter. So let's end this video here. I will be seeing you in the next lecture. Till then, please take care of yourselves, and thank you very much for listening.